Yeah, my name is Ujjwal. I'm a first-year PhD student at UC Berkeley. And today I'm going to talk about a new optimistic rollup called Specular. And what we're trying to do in this work is to solve some of the security and trust issues in existing optimistic rollups today. Okay, so I'll briefly cover the motivation, which I think everyone's familiar with, some of the background of existing optimistic rollups, some of their problems, and what our solution looks like. Okay, so we all know like Ethereum doesn't scale. You get 15 transactions per second, and that gets you like high congestion fees. And so what we're interested in is like how can we scale Ethereum throughput without compromising on decentralization. So one promising solution is, does this work? Oh, yeah. One promising solution is validating bridges or rollups where you offload transaction execution to an untrusted L2 executor, and off-chain execution state is checkpointed periodically on-chain, with the validity of the state guaranteed by either a validity proof, such as like a ZK snark, or a fraud proof. So I'm just going to focus on fraud proofs for today. And so in fraud proofs, basically you have an L1 contract which accepts a validator's state assertion optimistically, and other validators can submit proofs to L1 to the L1 referee to invalidate an incorrect assertion that they disagree with. So if the assertion is not invalidated within a time period, then it's eventually confirmed and considered final. And the key assumption here is that at least one honest validator exists to submit these fraud proofs. So more concretely, it looks like this. You have a sequencer. The sequencer sequences transactions. The executor or validator will produce these commitments or assertions. And a challenger can come along and submit a challenge if they think it's incorrect. And eventually, if no such challenger does that, then eventually it will be accepted at the challenge window. So if you look at like modern optimistic rollups today, there are like a couple objectives that they optimize for. You want low costs for normal execution when there's no fraud. And then when there is fraud or when there's a dispute, you want a reasonably low cost dispute resolution mechanism. And then the other interesting thing is we want a developer experience that is identical to L1. And we often see this referred to by, like, for example, the optimism people, they call it EVM equivalence. And so at a very high level, the common approach that you see in these rollups is you leverage an existing Ethereum client, and you use its EVM at L2 for execution. And then you secure the rollup state with an interactive fraud proof mechanism. So what does interactivity mean here? I'm not going to go into like all the details for time, but like basically during a dispute, a challenger and a defender narrow down their disagreement to a single step, and then they efficiently execute that step on-chain to determine the winner. And so if you look at, for example, like Optimism and Arbitrum, the approach that they're taking is they essentially add like a level of indirection where they have a lower level VM. And so how this works is you have like this Ethereum client, so for example, Geth, which you're all probably familiar with, and you adapt it to L2, and you compile that client to a lower level target, such as MIPS in the case of Optimism and WASM in the case of Arbitrum. And the resulting binary that's compiled is committed to on L1 after like Merkleization. And the interactive fraud proof basically enforces that the execution of the binary is correct at the target instruction set instruction level. So the key observation here is that the interactive fraud proof verifier is bound to a very specific binary that's output from this like entire process. And so if you think about it, like this has like multiple issues, right? So this architecture basically in its design completely prevents permissionless and trust minimized client diversity. And the reason that's a problem is because if you have like any bug or vulnerability in the client, then your entire network is impacted, and it completely prevents you from being able to detect an invalid state, for example. So that can, like, conceivably, like that can result in loss of user funds, right? And so this has like a couple dimensions to it. So first is like, because you're committing to a binary commitment, you basically have a permission system where only that specific binary can be used to produce these fraud proofs. So if I have a client that differs from this binary, and even though it's able to detect the invalid state, I can't use it to submit fraud proofs, which is a problem. The other dimension to this is that even if you try to introduce like a K-majority scheme, which has been suggested, for example, by the optimism folks, the problem is that you now have a majority trust assumption where you have to trust that K out of the n binaries are correct and agree on the state output. And so that's like an issue for users, right? Because like now you have to trust more than a single client, you have to trust multiple clients as well. And now it's also operationally complex for validators because they have to be prepared to run the interactive fraud proof for every single client program. Which means like as a validator, you need to be prepared to run like get, Besu, and like all the other clients that they allow here. So this scheme also doesn't really work. The other problem with this is that every user, every validator has to trust the correctness of the entire stack. So that includes like off-chain and on-chain components. So off-chain, you have to trust that the client program implements the EVM correctly, along with like all the L2 changes that they make to adapt it to the off-chain environment. And then you also have to trust this compiler that is used to compile to a lower level target ISA. So for example, like you have to trust that the Golang compiler compiles correctly to WASM or MIPS or whatever. So this is called the trusting computing base, and it's very difficult to audit because this is like hundreds of thousands of lines of code, right? You have to trust the client program and you have to trust the compiler. And it's also impossible to formally verify this code because like, I mean, how do you even begin to do that? And then the third problem is that you now have a frequently triggered upgrade process because every off-chain component that is changed or modified now touches the TCB, which means you require a security audit. And this also puts L1 governance on the critical path of the upgrade, right? Because if I need to perform an upgrade, even if it's just like a small performance change that doesn't change the semantics at all, I have to reflect that in the binary that's compiled. And that binary goes on L1, right? So you have to like go through L1 governance for that, and we know that can be hairy, right? You might have disagreements in the community, and so like that might be a tedious process. And then the other issue that arises from that is that if you have a governance-dependent upgrade process, then it becomes really hard to forfeit upgrade keys, right? Because if you forfeit upgrade keys, you no longer are able to ship vulnerability patches or performance upgrades. So people have talked about like people who develop rollups have talked about forfeiting upgrade keys, but it's very difficult in this current model. Okay, so what is our solution to these problems? Well, the key idea is very simple. It's basically just like before, we have Ethereum client at L2, so for example, Geth over here. But instead of having this level of indirection with lower level VM, we enforce EVM semantics directly, right? So what that means is we construct one-step proofs over the EVM state transitions at the EVM instruction level. And yeah, and so this is like a really simple idea, right? But it gets you really nice properties because now you have intrinsic client diversity to the fraud proof system where you can use any client which implements EVM semantics to participate permissionlessly in the dispute resolution protocol because we don't have like a commitment here that tells you whether or not you can use it, a specific client. And now, not only is it permissionless, you only have to trust that one out of all of these clients are implemented correctly. Because if even one implements EVM semantics correctly, it'll detect any bug that, any invalid state that arises from a bug in a different client. And now you have low operational complexity as well, because as a validator, you can run whatever client you want. You don't have to run like every single client that was like whitelisted in the previous approach. Yeah, so, and then the second property we get that's really nice is you have this really small TCB, which is entirely on-chain. And because it's so small, it's only like 1,000 lines of code instead of hundreds of thousands of lines of code, it becomes way easier to audit, right? And not only is it easier to audit, it's actually possible to formally verify because we can use existing tools like the KEVM to formally verify the one-step EVM simulator that's existing on-chain for the interactive fraud proof. Yeah, and then the third property is because we are only implementing EVM semantics in the verifier, we now have like a very infrequent TCB / on-chain upgrade process because if you change like something in Geth or Besu that only modifies performance or fixes a vulnerability which doesn't impact the semantics of the EVM, then you don't need to reflect that on-chain in any way, right? So you're only required on an Ethereum hard fork, and specifically an Ethereum hard fork which modifies execution semantics to change the L1 verifier. And so, yeah, so like I mentioned before, for performance improvements, for vulnerability patches, you can ship those without an on-chain upgrade. Yeah, and so now it becomes practical to forfeit upgrade keys because you can now make these changes without going through L1 governance. Yeah, so I'm not gonna go into all the details here, but I mean, it's like very simple, right? You have like so to achieve this, like all you have to do is you have the verifier verify the initial agreed upon EVM state between the challenger and the defender, and then you simulate the EVM opcode execution to get the final state, and you verify that the state is the same as the prover's asserted state and different from the defender's state. And so to do this, we just like, we check that the instruction modifies the stack, the memory, the storage, the gas, and like all the stuff in the EVM correctly. Yeah, and so the current implementation is like, it only modifies less than 100 lines of code in Geth, and it supports all inter and intra-transaction semantics defined by the Ethereum specification. So it is like what other people have called like EVM equivalent, right? And so so our system is the only one to take this like EVM native approach, and because of that, we get all these nice properties that we talked about earlier. But there's still like a lot of work that we want to look at to improve the system. So like I said earlier, we want to be able to formally verify the Specular TCB, which I said was possible, but we haven't implemented yet, but it's definitely possible. And we also want to improve on the normal execution fees and also the dispute resolution gas fees, which we can do with the help of snarks, or in the normal execution phase, we can do with the help of a data availability layer, and there's been like a lot of recent work on that helps. And we also want to work on sequencer decentralization and extension to other clients. So if you're interested, we have like a testnet running. You can try out the system yourself. And we're definitely looking for people to get involved if you're interested in all of these problems. So yeah, there's our contact info, and yeah, come talk to me later or contact me through one of these channels, and yeah, we can get in touch. Thanks.